let me show you what I saw. One person sent me this file, and then I replied to that person. I cannot remember that person, who that person is, but I'll just show you the code, and I put it into today's folder, so this way if I remember to upload it, it will all be here. Okay, this is a program that I saw. We'll just call this allocate, okay? Because that's all that I'm trying to illustrate here. So we have to put all your variables into the data section because we are going to change those memory locations. If you put into the .text section, that means you're not planning to make any changes to those locations. So this is where you need to put it. So I saw one person ask me a question and send me the code, and it looks something like this, .in x, .in 0, y, .in 23. Okay, I'll just use some non-zero values here, and then that person also had I being say .int and j .int and like that. Okay, and okay, so let me just go ahead and actually finish the program because we can actually see what is going on here. Once you see it from the GDB perspective, then oh, okay, so that's what that's what the assembler is doing when we have .int and .int, but with no values after the .int. And let's say turn on the line numbers. So the problem has to do with line 4 and line 5. They are syntactically correct, but they do something that people do not expect or normally do not expect. So what I'll do is I'm just going to finish up this program here. We are not even going to run the program, so 2 no-op instruction is good enough because we are not going to run it. I just want to show you the values of the labels. Okay, so we'll go ahead and do our usual stuff here. Allocate.o, oops, allocate.s, ld. Okay, so now we are going to go into the debugger. And as I said, I'm not even interested in running the program at all. And just to make sure that I can still do it, I can say set x equals 20, and it complains because x is not in .data. Okay, but it should be. Cannot access. Oh, because this is before I ran the program. That's right. So in order to do that, you have to run the program first. I think that will probably answer your question too. Because before you run the program, it is not actually loaded into memory yet. So as a result, you cannot access those locations. Okay, just to be sure, we put a breakpoint on line 11. Run the program, it stops at the second no-op instruction at this point. Then we say set x equals to 20, and it works. So I think that's the problem. When a few people mentioned that you could not set the values of the variables, that's because you have not even executed the program yet. So the first thing you have to do is to put a breakpoint right before your code, and then run the program. When it hits the breakpoint, then you can set the values. Okay. Yep.
Just to make sure, when you're setting x to 20, does it set x to 20 only in the debugger, but the value of the x would still be 23 or whatever it is? 5.
Nope.
So in actual file, it will be.
I'm not changing the source file. I'm just changing those 4 memory locations when the debugger is running, when the program is being run in the debugger right now. So I'm not changing the source file. The source file is still putting a 5 there.
But it would still look like you've changed it like 5 to 20.
For the rest of the execution of this program, yes, it will be using the 20 instead of the 5. And this is a good way to test your program because you don't have to reassemble or you don't have to change your program source code and then reassemble and then relink in order to test your program with different values. Okay. So I think I just killed 2 birds with 1 stone because now I can also look at I and j. Okay, so let's go ahead and print I and print j. Hey, they're the same. Well, let's take a look at the address of I and then look at the address of j. They are the same. Why is that? Because the .int with no value does not allocate anything. Let me go back and look at those lines.
So if it doesn't allocate anything, why do they still have a value of 1?
It's just by accident, whatever is in the dot data section after this dot int 23 turns out to have 1 as the value. But that's not guaranteed because it's actually not initialized memory. It is allocated because you might think that since I have dot data here and it ends here, the compiler should have complained or the debugger should have complained and say that that portion of memory is not allocated to your program. But memory allocation is by page in the system because we have virtual memory, so memory allocation is page by page. So in this case, a page is at least 512 bytes. So even though we are only using 8 bytes of it, you probably can access up to at least 512 from the label X before it will start to have a general protection fault saying that you're not supposed to access those locations. Okay. Any other questions? These are questions that I encountered. Yep.
So if you'd given J a value, I would have had J's value because the
Yes.
locations would have been the same.
Because there are 2 bookmarks on the same page.
So you just need to initialize it?
You just need to say .in0, just .in something.
Okay.
Yep.
That's fine.
If you're counting like a memory location, will you go like 4 bytes back for each of those then, or?
Sorry?
So say you had like your, like from start minus, 7 or whatever. Do you go 4 values back on each of those, or?
At this point or
Yeah,
later?
see if you're counting them. How many?
This is as if
They're not
we just
there.
have that.
Okay.
Yeah, .int with nothing after that is not allocating anything. It is still valid syntax, but it doesn't do anything. It's basically doing nothing. Yep. In other words, the program that we had before is identical to this program here. You're defining label I and J as the location right after the last .int 23, but it's not allocating any storage for either one.
So J minus 7 would be the first part of, the Y.
J minus, no, I and J are the same. J minus 1 will be the most significant byte of this .int.
Minus 1.
Minus 1, because it's little endian. Yep, you had a question?
Yeah, when the value, I think the dividend is negative, your program at the end, and it's written this way, the remainder is negative and the divisor is positive. Okay, I'm just making sure when you grade it, you know that.
Yep.
Okay.
Yep.
Yeah, I had to go back a minute and see, yeah, it does that.
I was gonna fix it in mine, and then I thought, no, I'll probably just.
No, because I go by the C code, the behavior of the C code. So
Okay.
your assembly code has to be consistent with the behavior of the system.
Okay, good.
Yep. Any other questions about the homework assignment? Yep.
So when I take the program, I take 4 divided by -3, and I get the remainder equal -1. That's your code, correct?
What is the quotient? 13?
-1, I think. I don't remember like. But we have 4 divided by -3, and then the remainder equal -1. Is that still fine? It can be, right? But it's how your code works.
Yeah, it would be a quotient of 13 with a remainder of -1 still. So that's correct.
Yeah. It's a negative.
Okay, so what how the code works is, if the device, okay, the only thing I want to stay positive is the divisor. So the divisor stays positive.
Yep.
If the divisor is negative to begin with, I flip it to the positive side, but I also flip the dividend to the opposite sign, whatever it was.
Remainder?
You mean the remainder?
Remainder is the same as dividend.
Oh yes.
Yeah. So that's why it get flipped.
Phillips -1.
Right. Because the divisor, yeah, so I have to keep one as in one particular sign for this to work. Yep.
I already turned it in, but I didn't finish it to the 100% of what I wanted it to be. Can I still finish it and then turn it in? Or
Yes, you can.
Okay, so
Yep.
with the penalty then.
But I will use the last submission date that you use.
Okay, so
Yep. Go ahead.
The upload area on the site closed, like as I was turning it in.
So I just emailed it to you, is that okay?
Well, that means it's a little bit past the deadline already.
It was
at that
literally
time.
like 10 seconds.
10 seconds.
It's like when I loaded the page, the upload area was still
How
there,
about
and
you-
then I
how
was
about
like,
you-
"Oh, upload?
How about you just
Send,"
upload it
like a
sometime today?
bird while sending it
What
out.
what if I say this? Any time today is still counted as on time.
All right.
I can see a lot of people disappearing
Well,
right now.
How do we send it in?
Hmm?
Because there's no upload area.
There's one. I just changed the due date.
Oh.
Yeah, as soon as I changed the due date,
We could get extra credit if we already turned it in.
A lot of hagglers.
Welcome.
All right, so I think the homework assignment is okay now. Okay, because I just pointed out a few pitfalls that people get into, and it really is just tedious. It really is just tedious. You don't have to use the translation mechanism that I talked about in the class. So if you want to turn it into something that's different, but it will do the same thing, that's okay too. It's just that I prefer a particular way that is consistent and it does the same thing every single time. But if you have some other way to look at this and you think it is more convenient and make it easier to translate the algorithm, that's okay too. But you do have to preserve the meaning of the C code. In other words, you cannot just learn how to use diff-L and replace it with a single instruction. All right. So, yeah, question?
Yeah, really quickly. What if you submit it like before this due date and then resubmit it just to fix something? Would it still be counted as late?
Yes, it would. So it depends on how bad is the problem. If your problem is really bad, like the program is not going to work, because the way I grade this homework assignment is I will feed it test cases, and it's just the number of test cases that works is going to be the proportion of the points that you get to keep, not counting the late submission discount.
So it's not even the code itself, translated code.
I'm going to grade it by its functionality. Does it function the way it's supposed to? In other words, it's not an effort-based, grading. It's a result-based, grading. Is that okay?
Doesn't matter if your fingers were bleeding when you were done with that. It just matters if it runs.
And also, does it the way that it is specified, and then go by all the same, conform to all the basic rules. All right, so we're gonna let this go for now, and then we're gonna take a little vacation now. In other words, we're not gonna talk about some actual coding stuff, but we'll start to talk about some concept stuff. Okay. In other words, we're moving on to section 6. Now, section 6 does have some real coding stuff, but it's real easy. Okay, we don't have anything quite as convoluted as what we just talked about, in the past few weeks. The first thing I want to talk about are interrupts and system services, and then we have a Linux system call table, which is really just a lookup table. And then we'll start to understand how do we use system calls inside assembly language programming. So let me ask you a question first. How do you print in C++ programs? Cout, right? How do you read something from the keyboard, so that you can interact? Cin, yep, Cin, Cout, pretty easy stuff. But what do you think the system has to go through in order for it to print something to the screen, to the console? Yep.
Open up GDB and then type in X.
That's not what the system does. That's what you do.
Well, I'm just guessing. I don't know what it does.
Okay.
You mean what's an alternative of Cout and Cin in assembly?
No, I'm just asking, the back end of Cout. What is the back end of Cout? Okay, let me rephrase the question. Cout is a special what? It is an object of what class in C++? OStream, right? It's an output stream. Okay? So output stream as a class is used to model what? Yep.
Is it Std Out?
Std out. Very good. And std out itself is what?
No idea.
Well, to the operating system, what is std out? It's a file. Okay? It is a file. In other words, every time you want to print something to the screen using cout, you're actually interacting with a file. And the file is commonly known as standard out or stdout, standard out. Okay? All right. So that means we are actually using file-based operations to print, and when you want to read something, it's really the same thing. It's a file-based operation to read from the keyboard or what you type as well. Okay. How do we interact with files? In assembly. First of all, is it even possible? How much trouble do we have to go through to deal with files? Not that much. Okay. And that's because the kernel or the core portion of your operating system has a built-in capability. It gives you surfaces, and one of the surfaces is to say, okay, just tell me what you want to do with files, and I will try to do it. Okay, as long as you're allowed to do it, I will do it for you. So the operating system is acting as a proxy. So you do not deal with files directly. You ask the operating system to do it for you. Are we doing okay so far? I want to change the kernel, the bootstrap, file, and plant a virus in it. Do you think I can do it?
Let's talk about that.
Let's talk about that. As a regular user, you have no access to the file. At least you don't have any write access to the file, and you cannot modify it. So that means the kernel is not only providing surfaces, but it's also double checking to make sure that you, in fact, you are allowed to perform those operations before the operations are actually performed. Okay, so we have to interact with the kernel, the operating system, in a way so that the kernel can do what it needs to do, but it will not give you access or privileged access accidentally. Okay, is that concept doing okay so far? So that means a regular function call is not going to work. Because if you think about it, if all the system surfaces are implemented as nothing more than subroutine calls, that means when you make that subroutine call, you can do whatever. You can ask the operating system to do whatever you want to do, including clobbering, protected files and stuff like that. Okay. So keep that in mind, when we talk about this particular topic. Before we even get to that point, we'll talk about something that seemingly has nothing, absolutely nothing, to do with file operations, input, output, and that sort of thing. It has to do with interrupts, and we'll see how interrupts can be related to what we have to do in this case. All right, so let's go ahead and start with interrupts. We start with section 2. Which is live without interrupts. Well, in software development, that is. Yeah. Interrupts are bad in most cases, but in software, interrupts are actually a very useful concept. All right, so just imagine that I'm the processor. Okay, I'm the processor in my office. I'm doing work, and it's my office hour. And so I'm expecting students to be coming by and asking questions and stuff like that. But at the same time, I want to use that time to do some of my own work, like giving you guys new homework assignments and so on and so forth. So what am I going to do? Well, I sit in my office, I do what I do, and then when you guys show up, you just knock on the door, and I just put down what I'm doing, and then I'll answer the questions. And when you have what you need, then you leave. Then I will continue to do what I was doing before. That's the usual way that we do things. Yep.
So we're just interruptions to you?
You guys are definitely interrupts.
That was a perfect example.
Yeah.
Good enough.
Okay, so what if I cannot take interrupts? In other words, what if there's no way to get my attention, to divert my attention to do something else? Well, then we have to do something that's really tricky. I can sit in my office and say, and call out to the hallway, is anyone waiting? No. Is anyone waiting? No. Is anyone waiting? And I will spend my entire hour asking that question. you know, just in case someone walks by and have a question, well, they want to
You
ask
should
me.
do that.
I can record it and put it in the loop, and I'll just leave my office, you know, close the door. Okay, that's called polling. Okay, and that's how, you know, operating system were, you know, in the good old days of CP/M and DOS. In other words, DOS, disk operating system, which is the predecessor of Windows, you know, and a successor of, you know, CP/M. When it needs to interact using the command line interface, it needs to know what you're typing, right? I mean, this is back in the good old days, you know, where we don't even have USB, we have dedicated, you know, keyboard ports and stuff like that. So the operating system has to ask, okay, it needs to know when you type something. That's what it needs, right? So that when you type, you know, dir, press the enter key, it knows that it has to, you know, list the directory, and, you know, and then go back to the prompt and then wait for you to enter some more stuff. But in those days, there's one main difference between the early DOS and Linux. What is the main difference? Or there are several main differences. Just tell me a few. From the perspective of the keyboard and the command line interface. And also look at this from the power server perspective and not just your virtual machine. What is special about the power server that is not the same as your virtual machine? It has to serve multiple people. Okay? It has to serve many, many different people at the same time. Okay? And your virtual machine is serving mostly just you. I mean, you may open up your multiple PuTTY terminals, but there's still only one user. Back in the DOS days, it's even simpler. Life is really, really simple. Because back in the DOS days, not only is the system intended for one single user, it's also a single session. In other words, you cannot open up multiple terminals and do different things in different terminals at the same time. You only have one single console window, and that's it. So that means, you know, you can use very simple approaches. And that's exactly what DOS does, is to use polling. Instead of asking, is someone waiting for me in the hallway, it's asking, hey, Mr. Keyboard, do you have anything for me? And they keep asking the question. If the keyboard, you know, controller says no, there's no key press events, then the operating system would use a tight loop and come back and ask that question like right away. Is there a keystroke for me? 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 It would just keep asking that question in a very tight loop. What does that do to the processor? It will heat it up because, you know, it's spinning in a very tight loop. It's actually doing something. It's just not something that is useful. In other words, it is executing instruction. It's accessing memory. It's doing all that stuff, but it's not very productive. So it does heat up the processor. It will still use up, you know, energy in order to execute those instructions. But it was okay because, you know, DOS was intended as single user and single session. There's nothing else going on, right? And then Windows come along. Okay, Windows 3.1, Windows 3, and then Windows 3.1, and then Windows 95. They all share the same property. Has anyone tried to use a DOS prompt in any one of those versions of Windows? What happens when you start up a DOS prompt?
Switches to it.
Everything slows down to a grinding halt, right? In other words, you can open up, let's say, you know, Excel, you know, as a spreadsheet, and you can, well, Excel may not be the best example. You can open up some application that will do something, quote unquote, in the background. So without interaction, it will do something like animation and stuff like that. And as soon as you open up a DOS prompt, those other programs will just slow down to a grinding halt. You know, sometimes it just stops completely. Do you know why?
Polling.
Because of polling, exactly. Because Windows 95, 98, and all earlier versions of Windows doesn't have a sophisticated way to share processing resources. It uses what we call cooperative multitasking in order to give you the pretense that it's doing multiple things at the same time. In other words, let's say I'm one application, you're one application, you're one application, and you're one application. We have 4 applications, you know, loaded and running in the system. Windows says, well, you guys have to play nice. Okay, so tag will run use the processor for a few milliseconds, and I will go like, oh, I use up all my time already. I better pass that time to you. So you have to do the same thing. You just time yourself. Oh, okay, I have run about 5 milliseconds. It's time to move it on to the next person to the next person, and then back to me. So we basically just voluntarily give up control of the processor, and as a result, it seems that all 4 programs are executing at the same time. That's called cooperative multitasking. But what does DOS do? A DOS prompt. It hogs the processor, doesn't it? Because it has a tight loop. It's not. There's nowhere in the DOS prompt that says I'm going to give up control. And that's why the DOS prompt, being me, once I get control, I'll just say, is there any keyboard event? Is there any keyboard event? Is there any keyboard event? And all 3 of you will have to wait indefinitely. Because I'm not passing control to you. Do you see the problem with polling? Okay. Well, later on, I think in Windows 95, the later versions of 95, or maybe the earlier versions of 98, they actually try to make it so that there's a certain type of timer. So when a DOS prompt is running, there's a little timer that goes like tick, 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 ding. Okay, we have to take control away from TAC and pass it on to the next person. But I'm still chewing up processing resources because you may have something to do, but it will only take you 500 microseconds to do. You have another thing that will take you 2 milliseconds to do, and you have another thing to do that will take you 1 millisecond to do. Then control is getting back to me. And I'll just hog the processor for as long as I can, just asking, is there a keyboard event, is there a keyboard event, is there a keyboard event, until the kernel or the operating system forces me to give up control and then give it to you. So in terms of process load or processor load, it's still way up there. I'm just spending all this time asking that stupid question. Is there a keyboard event? Okay. What does that do when you're running this on a laptop computer?
Turn it into a slot.
Well, you better bring along a little trolley to carry your battery, because it's going to chew up your battery. It's because it's using processing time the whole time. Now, when Windows NT come along, the command line interface of Windows NT, even though it may look the same as in the earlier versions of Windows, the mechanism is completely different. Because Windows NT, the kernel, uses an interrupt-driven mechanism. In other words, nobody is asking that question, is there a keyboard event, is there a keyboard event, is there a keyboard event? Instead, the operating system is going to configure the keyboard controller and say, hey, Mr. Keyboard controller, I'm going to leave you alone, but if there's a keyboard event, wake me up and get my attention, and then we'll process it. Okay? So after that, the operating system can go about and do just about anything it has to do. What if, in this case, remember the 4 programs, the 4 processes? What if you have nothing to do, you have nothing to do, you have nothing to do, and me as a command line interface also has nothing to do because no one is pressing any keys? What do you think the processor would do? It goes to sleep. And what does that do to your battery life? Yeah, it saves the battery life. Now your battery can last a lot longer because we are not wasting all the energy asking that stupid question. Okay? So what if I type something on the keyboard? What if I just click a mouse or press a key on the keyboard? Well, first of all, the keyboard controller is going to realize, oh, there's an event coming in. The keyboard event is really just encoded as the key code either being pressed or being released. Okay, it doesn't even map the key code to the actual key because it is up to the operating system to decide how to interpret the key codes. But in any way, it's really just an event. So the keyboard controller will generate an interrupt. In other words, the keyboard controller would then say, okay, I got an event that needs to be handled. I don't know what to do with this key code. The operating system does. So then the keyboard controller will raise an interrupt. Okay? So we are already done with this portion here, and we are starting with interrupts. So what happens is, on the processor, on any processor that supports interrupts, it has a special line. There's a trace. There's actually a pin, that is corresponding to interrupts. When that pin is asserted, in other words, asserting means, when that pin is. This is a little bit tricky because that pin is usually using an inverted logic. In other words, it's normally high, and when there is something to take care of, it has a low voltage. But at any rate, when it is asserted, then the processor will go, it will go, okay, I need to process some hardware event has happened. Are we doing okay so far? So this is something that you can actually see on an oscilloscope. The interrupt line is going to get, a state change. Do you think the keyboard controller is the only device that can generate interrupts? Not by a long shot. What else do you think can generate interrupts? Back in those good old days, when we have
Mouse,
the mouse.
speakers.
Back in those days, we have modems.
What's that?
Yeah. Modem is a modulator demodulator. That's the that's the name of a modem, right? We have printers. We have parallel port printers, and for the longest time, parallel ports do not. They have the mechanism of interrupts, but the software driver does not implement it for the longest time. So it's using polling too. In this case, it's telling the printer to print something, but the computer can feed information a lot faster than your poor 9-pin dot matrix printer can print, right? So for the most part, your computer can say, oh, print these dots. And then your printer will go like, like that, right? Then what does the computer do? The computer can feed it so much faster. So your computer will feed it, like a whole bunch of dots, and then go like, are you ready yet? Are you ready? Are you ready? Are you ready yet? And then the printer, after it prints a whole line, will come back and say, yes, I'm ready for another line. So the computer will give it another line to print, and then the operating system will just keep asking the question again. It will use polling to see whether the printer can take another line or whatever the buffer length is to print some more. And the interrupt changes everything, because with interrupts, the computer will feed the printer port as much as it can, and then when the printer has no space left in the buffer, the operating system will inform the printer, or the printer port in this case, and say, when you're ready, come get my attention. Then the processor can go and do something else, right? So now we have all these different devices that can generate interrupts. The processor has to find out who generated that interrupt, who needed attention to surface a hardware event. Yep.
Why is the interrupt pin high voltage normally? It seems weird to me that they would do that.
That has to do with electronics, because, okay, since you asked the question, I am obligated to answer the question.
Sorry.
Here we go.
Okay. So typically, in the very, very good old days, okay, an interrupt line would look like this. There's a resistor to pull it up to 5 volts. Back in the old days when they still have TTL, CMOS, logic operating at 5 volts. But now you have multiple devices that can hang off the interrupt line, and each device can pull this to ground. So you can use one single interrupt line and share that with multiple devices easily using this pull. This is called a pull-up resistor, and so using the pull-up resistor, you can very easily share the same interrupt line with multiple devices, which actually is the next topic. When the interrupt line is asserted, how do I know which one or which device is requiring some attention? Yep.
So does this have to do like on older computers? You used to have IRQ settings in the BIOS.
Yep.
or, like,
Yep. But IRQ is already a very advanced fairly advanced topic, because in the good old days you only have one single interrupt line and with multiple devices. This is before PCs. Okay, the first PC already has multiple interrupt lines, but you can have one single interrupt line and multiple devices, because the processor can now go and ask, oh, did you ask for my attention? 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 So the processor can actually go through that process and figure out which device was the one that generated the interrupt. You can have multiple devices generating an interrupt or requesting service at the same time. The processor will just have to ask it in order and surface those devices. And then later on, we have multiple interrupt lines. In other words, if you have 4 devices, it doesn't look like this anymore, and it looks more like this. So each device has its own interrupt line going back to the processor. So now it is easy to surface the interrupt, because if it's coming in from this line, it has to be the keyboard controller. If it's coming in from this line, it has to be the printer port. If it's coming in from this line, it has to be the serial port, which is usually connected to a modem, and so on. Okay? So that's basically the low-level view of interrupts. Okay, but we already know it's not a good idea to let end users have access to everything in the system, which was also the case in the good old days of DOS and early versions of Windows. In the early days of Windows, like Windows 98 and all the versions before, I believe this also applies to Windows ME, Windows Millennium. I guess that was one of the worst versions of Windows before Vista. So in those days, what happens when one program decides to misbehave and start to access locations all over the place and try to corrupt stuff all over the place? It actually do it. It can actually do it, right? Because there's no memory protection. Okay, so let's say 1, 2, 3, 4. Once we have the 4 programs that are running, 4 processes. Well, guess what? We share the same common pool of memory. So when it is my turn to execute, I can choose to take your notebook and trash it, throw it into the shredder. So by the time return control get back to you, you will get a surprise. Okay. What about the operating system? I mean, we are applications, right? Surely the operating system has its own stuff that is locked up. Not the case. Okay, that's not the case in early versions of Windows. The operating system is also using the same resources that all the application programs have access to. So when you crash hard. Whereas in the current version of Windows, okay, all the NT-type Windows have the operating system running in a protected mode. So applications can crash and crash itself. They can't even crash each other easily. And nobody can crash the kernel or the operating system except for device drivers. Those are nasty too. Okay? But how does that happen? But now we have a problem. We have a big, serious problem. Because on one hand, we know that the operating system, including the device drivers, need to have privileged access to hardware, because otherwise it cannot get the job done. But we also know that applications should not have access to everything, should have very, very limited access to system resources. Definitely not access to direct I/O devices and whatnot. So here's the question. This is the scenario. I'm an application running, so I'm gladly doing my things, and I even refuse to give up control. Okay, I'm just hogging the resources of the processor as much as I can. So as I'm doing my own processing here, the keyboard controller decides, oh, I got an event. What do you think will happen at that instant? Well, the interrupt happens, okay? And when the interrupt happens, the processor will get notified and say that, oh, there's a hardware device that requires your attention. Okay? But I'm the program that is running right now. What is the operating system, or what is the processor going to do? Well, the processor will first identify which device generates the interrupt. It will identify which line is generating the interrupt. It will use a lookup table and find out, okay, the code or the program to handle that interrupt is over here. And then it will go try to execute that code. But now we have a problem, because when I'm running, I have to run at a low privilege level. because they know that tech will try to corrupt some other programs, trash the kernel and stuff like that. So they have to lock me in a cage, right? But in order to surface the interrupt, whoever is doing that cannot do it in the cage. Because whoever is going to surface the interrupt needs direct access to the operating system, memory of the operating system. It needs access to the I/O ports so that it can actually read back the key code and also reset the interrupt flag and stuff like that. All of those are privileged operations. But yet, when it happens, the processor is in a cage because it is executing code in an application. So what needs to happen is in the hardware, the processor will elevate itself to a much higher level of access before it executes the code that surfaces the interrupts. Okay? This is all done in hardware. Once you configure the processor to do it, it will do it. So let's go through that exercise again. Okay? And we'll draw a little picture here. All right. So this line represents the application program executing, and right at this moment, there's a keyboard event. The interrupt happens. When the interrupt happens, this program will be interrupted. And what happens is the processor will save the PC or the program counter along with some other stuff so that it can come back later on and continue execution at this point. So that the application program will not even notice that something has happened by the time control is back to it. But at the same time, what the processor will do is it will elevate the privilege level to the appropriate level, and then it will look up the address of the handler of this interrupt, and then execute the interrupt handler. Are we doing okay so far with this concept? It will take whatever long it takes to process the interrupt. When the interrupt is processed, then it will get its privilege level back to where it was, and then continue execution from the application's perspective. So the application will never notice that an interrupt has even happened. But the interrupt service routine will get the privilege level, will get the privileges that it needs in order to execute the code. Are we doing okay so far with this? The rationale behind the elevation of privileges. That's okay? All right. And that's basically summarized by this particular slide here. ISR stands for interrupt surface routine. They're really fun to write. There's a lot of cool stuff you can do with ISRs. And then device side, we don't really have to deal with the device side too much from the software perspective, because for the most part, you really can't do much on the device side. Okay. And then we talk about the advantages of interrupts. The advantages is, one, the program that is being interrupted doesn't even know that it is interrupted. Okay, now how do we know that? Now this is a command line interface. I'm in VI right now. What do you think happens when I move the mouse around like that? It generates interrupts. But the application doesn't even know that these interrupts has happened because it doesn't need to know. Okay. So are there any questions at this point about the concept of hardware interrupts that you use to handle devices? No questions? Okay. Then we'll go on and move on to the next topic. The next one is privileges. This part talks about how we require different levels of privileges. So when you're running an application, testing your program, you probably want your program to run with low privilege level so that when your program doesn't work, it doesn't crash the entire system. But when the interrupt surface routine handler, or the ISR, the interrupt surface routine, runs, it needs the higher level privilege because it needs to interact with the I/O devices. So that's why there are levels of privileges. And you have to, the interrupt mechanism has to elevate the privilege level and then be able to return it back Because what happens if the hardware forgets to return the privilege level back to where it was before the application continues running?
It doesn't continue the application that was interrupted.
Well, the application will inherit the elevated privilege level. So now we have a dangerous situation again. Okay? All right. So that's basically what this slide talks about, is why do we need multiple levels of privilege levels, and why do we need a mechanism to automatically elevate and return privilege levels. So now we want to talk about system calls. What a system call is just a way to ask the operating system to do something. For instance, you can ask the operating system to open a file, to write content to a file, to read from a file, and then close a file. Are you guys all familiar with basic file operations like that? Open the file, do some I/O, close the file. Okay? But obviously, we cannot do everything. We cannot let an application do everything that it requests, because as I talked about a little bit earlier, what if I decide to trash the boot image of Linux? Well, I should not be able to do it as an application. So when the operating system is providing service, the operating system needs to run it at a privileged level because it needs access to all the resources. But it cannot let you gain the privileged level either. Are we doing okay so far? Okay. Remember this picture? We have exactly the same picture here. Your program is running along using the low privilege level. At some point, you want the operating system to do something for you. But in order for the operating system to do that for you, it needs a higher privilege level to do whatever you need to do. But after that, when the operating system returns back to you, it also needs to remember to lower the privilege level back to where it was. Look at these two pictures. They're the same. And yet, one corresponds to hardware events, and the other one is basically what your program is actively requesting. Are we understanding those two concepts? The first one is also called asynchronous. In other words, there's no way your application can know when an interrupt may happen, and that's why it's called asynchronous. In the second case, it's also called synchronous because it is your program making an explicit request to the operating system to perform a certain operation. But yet, even though one is asynchronous and one is synchronous, we still need the same mechanisms. Namely, we want programs to run at a lower privilege level most of the time. In order to do certain things, it has to elevate the privilege level to a higher level. When that is done, we also want it to be able to return to a lower privilege level. So how do you think they solve this problem? Instead of a hardware-based interrupt, we now have software interrupt. What is the first three letters of interrupt? INT. Have we seen that instruction? Not .int, but INT. We have seen INT.
Yeah.
That's basically what it is. It's a software interrupt instruction. When you execute an instruction, it is as if a hardware device has requested interrupt. It will go through exactly the same motion, except in the case of the INT instruction, your program is in 100% control of when it happens. Are we doing okay so far with the concept? Connecting the hardware interrupt concept to the software interrupt concept. Okay.
So that's why we have it's usually we have in 0x something at the end of the.
Well, we have
right?
this explains why it is int because it's an int
right?
because it's a software interrupt.
Oh, yeah.
But it doesn't explain what the second part of the interrupt instruction. When we use the interrupt instruction, it is int, and then we have $0xA0. This part controls where do we find the handler of this particular interrupt, and it is chosen by Linux, the Linux development community, that this will be the entry point for all Linux kernel type requests. Okay, because there are multiple locations. There's another interrupt at, I think in DOS, a famous interrupt location is 13 or 13 in hexadecimal, and another one is 21, I think. Interrupt 21 is also famous, for DOS applications. You can actually look that up. I think those map to BIOS calls. In other words, your BIOS, the PCI cards and other devices that you plug into your system, each one can also have its own subroutines associated with the device. And the BIOS calls are done through, I think, interrupt 21 in hexadecimal. And you can find lots and lots of documents for that. Let's take a look at this one. And we just want to find out what it does. Okay, so you can use the software interrupt in this case to read one character from the standard input, the keyboard, and echoes it to the standard output. So that's what happens when you use interrupt 21 and with a value of 01 in register AH. Sorry? Oh, okay. So now the next question is, what does it do when we have this code here? This is not working. Probably won't make it.
Oh,
ooh,
nice.
Cool, made it.
Gold stuff.
Okay, this is move L $1 into E AX, and then we have move L $0 into %E BX. I'm hoping that some of you still already start to recognize these three instructions because they're at the end of every program that we write, except for the programs that I know that I won't run it to the end. Well, as it turns out, what value you put into EAX specifies what do you want the kernel to do for you. A value of 1 means this program wants to exit. It's time to get out and free up all the resources. Once you determine EAX, register EBX is kind of like a supplementary kind of register. It's kind of like a parameter. In this case, it specifies the exit code. Do you want to exit with a code of 0? Do you want to exit with a code of 1, 2, 3, or whatever? Register EBX, is going to specify that. In other words, this is equivalent to doing this in C. Okay? Are there any questions about this part here? But why can't I just use a return to the operating system? Why do I need a software interrupt and ask the kernel to, so that this process, will stop existing? What is so privileged about this operation? Yep.
Because you're going to be deallocating memory?
Yep. So can I deallocate my own memory when I'm an application?
You can, but after you quit, it's not yours anymore.
There's nothing to return to, too. If you think about it, there's nowhere to return to. Because the operating system is not calling an application. The operating system, when the process starts to exist, there's no point of returning. It doesn't do it by returning. So you have to ask the operating system to do it. Other things also include, if you have any type of file handles open, this operation will close all those handles and make sure that a file that you open in your program does not remain open when the program itself has already exited. So are we doing okay so far with the concepts? Okay. Now many of you, or some of you, have asked, but how do I print something, in an assembly language program? Well, system calls. Okay. And what we'll do is we'll go to a table and find out exactly what can we do with these system calls, operating system calls. And I hope this link still works because sometimes they get moved around and not work anymore. Ah, still works. Excellent. Okay, so we'll just go ahead and magnify it a little bit. And these are all mapped to interrupt 0x80 on the i386 type architecture. So what this tells you is if EAX has a value of 1, the name of the system surface is exit. And this is the source code in the kernel to implement the exit call that you know in C. But it also tells you what other things you can specify. So in EBX, you can specify the first parameter of exit, which is the exit code. Is that okay? What about file operations? If you want to open a file, you want to use system surface number 5. And when you use system surface number 5, EBX will contain a pointer to the file path that you're trying to open. And the other two registers, in this case ECX and EDX, will specify, I think one controls the mode of the open operation, and then the other one controls the flags of the open operation. Now what if you want to find that out? You just say man to open. Now in this case, it is important to specify the 2 here, because open is a very common word. In other words, there are multiple pages in the manual that uses open as a title. This says go to chapter 2 and open up the help topic of open in chapter 2 open. And that's basically the open call. You can see one controls the flags and one controls the mode. And we don't have to deal with this, but in case anyone wants to open the file in an assembly program, the flags are basically saying, are we only reading the file, or are we opening the file just for writing, or do I need read-write access to the file? The mode controls whether you're appending to the end of the file. Async only deals with I/O devices, and a few other things that you can look into. But these are things that you can do in a regular C program, and now you can do it in assembly language programs too. Any questions about this part? What about reading and writing? I want C in and C out. Well, let's look through the table and see if you can find something that resembles what C in and C out would do. Just look at this page here and tell me which one do you think may be related to that. System surface number 3 is read, and system surface number 4 is write. Those correspond to file operations of reading and writing. Well, let's take a look at what reads requires. So what we need is EAX to have a value of 3. But what else do we need? Now, obviously, you cannot just say read and what file are you reading from? How many bytes are you reading? Where do you want those bytes to go to once it's read? You have to specify all those parameters as well. So when you're using system surface number 3, you will also use up 3 other registers at the same time. Now, let me just change the font size here because I need to display the other how we use the other registers. You can see that in this particular row, I'll just go ahead and highlight the entire row. Okay. So what we know now is we need 3 parameters. One parameter to specify the number. No, this one specifies a file handle or file descriptor. The second one specifies where are we going to store the bytes that we are reading from that particular file. And then the last one specifies how many bytes are you trying to read. There's no guarantee that you can read all those bytes, but how many bytes are you planning to read? Okay, so those are the 3 parameters. But when you look at unsigned int, char, pointer, and size t, it doesn't really tell you what those registers are used for. So what you need to do is to go back to the man page, this time use man to read, and you will see the C version of this and also an explanation of these parameters. The first one is FD, the file descriptor, which basically identifies which file you're reading from. The second one is a void pointer to buff, which is pointing to a place to put all the content that you're reading from the file. And the last one is count, which specifies the number of bytes that you are attempting to read from that particular file. So can everybody see how to correlate this table, what you put into EAX and what you put into the other registers, with a more legible, a readable description of the system service? Okay, let's try it. Okay, let's write a very simple program, and the only thing it does is to read something into a certain buffer, and that's it. now we go to another prompt and you'll start to write this little program. 0308 10. And we'll just call this program read.s. Now when you're reading, you probably want to allocate something in the .data section just so that we can store whatever we are reading in. And we'll just call this buffer. And we'll give it, I don't know, 32 bytes. Well, I have a better idea. Instead of using 32 here, I could use something that is kind of like pound defined, except it's not pound defined. Okay, we can say buffer size equals to 32, and then I can just use buffer size here. Because it's a label, and if a label is defined to be whatever integer it is, then every time the assembler sees that label, it would just be using the definition of the label. In this case, it's 32 for buffer size. We can switch back to text, define the entry point of the program, and then we can start to perform what we were about to do. The first thing we have to do, well, the order is not important, but you have to initialize all the registers that the system call requires. The first one that I usually do is EAX. In other words, if you initialize EAX to 3, it means to the operating system, to the kernel, it means read operation. We are specifying a read operation in this case. So this specifies a read operation. We also need EBX to contain the file handle. In other words, we need to tell the operating system which file are we trying to read from. Oh, Tag, you forgot to open the file because you have to open the file before you can read it. Well, there are 3 files that are always open by the time your program gets control. From the perspective of a C++ program, what are those files? Or how do you call those files as I/O streams? cin, cout, and there's one more that probably you do not know is cir.
And clog.
Oh, clog is the 4th one?
Yeah,
Okay.
there's a 4.
Okay. So there are these files that are automatically open when your program gets control. The file descriptor of these is just the way that was listed. 0 is standard in, 1 is standard out, 2 is standard and log is 4.
Log still goes to error. I was just being facetious.
Sorry?
C log still goes to C error. It's just
Oh, it's just the
just
same name.
different buffering method.
Oh, okay.
But it still exists.
So it's still using file descriptor 2.
Correct.
Okay. But if you're reading, which one do you read from? What should I put here to initialize EBX? What should I put here? 1. Well, 1 is standard out, which means it's intended for output. It's 0. Okay, we want 0 to specify standard in. We also need some other stuff here. What does ECX store? Okay, let's go back to the. It's like a char pointer. ECX is the char pointer, which there's actually a discrepancy here because if you look up the C code, it is actually a void pointer. But in assembly language, there's really no type, whatsoever, so it doesn't really matter. This is a pointer pointing to where you want to store the bytes that you're reading in. In our program, how should I initialize that? What should go into ECX? And let me just write the comment first. Specifies where to read the bytes to. It is a location. And it's probably a location in the .data section. So what should I put here?
Buffer size?
No. It's $buffer. Okay? Because if you specify buffer, then it will grab the first 4 bytes of the dot fill and then treat that as the address of where you want the bytes to go, which will probably be location 0, and then when you run the program, it will give you a general protection fault. But $0 specifies the label itself, the definition of the label itself is the operand, is the first operand, and that is the address of where we want to put the bytes to. Okay, we have one more to initialize. We have to somehow initialize EBX. It specifies the number of bytes, or the maximum, I should say, the maximum of bytes to read. And what do you think we should put here? Well, buffer size is a good one. I can always specify anything that is less than or equal to buffer size, but buffer size is good. Okay, well, we're done here. It's time to exit the program, right? And this program should work. What am I missing here? I initialize all the registers, and I forget to ask the operating system. In other words, I walked into a branch of the government, I fill in all the forms and whatnot, and then I just walked out. And not ask the clerk over the counter and say, please process this form. So we have to ask the operating system to process it. Okay. Are we doing okay so far? Separating the initializations of the registers, which is all good. It's like filling in a form. You would definitely need to do that. From the interrupt itself, which is actually saying, okay, kernel, I think I have specified all the operations that I want to perform. Go ahead and please do it now. That's the int instruction.
Okay, so whenever you call an interrupt, depending on which state you're in, it's calling for it to go into the next state. So the first time you're calling it saying, hey, make me priority, higher privileges. And the second one saying, okay, drop back down to lower privileges.
It's all done automatically. In other words, when you execute the interrupt instruction, the int instruction, the first thing it does, or among the first thing it will do, is it will save the location where to come back to, because otherwise it won't be able to come back to continue the execution of the program. So it will do that, just like with a hardware interrupt, it will do the same thing. And then it will elevate the privilege level, and then by the time it gets to the subroutine at whatever subroutine that the 0x80 the vector table is pointing to, then the kernel has control at that point. Then what the kernel does is it has a huge switch statement based on the value of EAX, and then in this case, since we put 3 into EAX, it will use the switch statement to go to the code that will deal with reading a file. It will do whatever it needs to do, and when it's all done, it will return control back here, and also get the privilege level back to where it was. Okay. So the int instruction is really quote unquote a call, a call mechanism, but it's not a regular call because you also have the changing of the elevation and also the return of the privilege levels.
Okay.
So we'll go ahead and assemble this program and run it and see whether it works the way it is supposed to. So we'll go ahead and GDB the program. You can actually run the program by itself, but it doesn't really give you any output, so it's not really that much fun. So we'll go ahead and put a breakpoint on, let's put a breakpoint on line 13, after the interrupt call, and we'll just go ahead and run the program. Well, it's not returning because it's waiting for you to type something. So the question now is, when do you think the program will continue execution? As soon as I type something, or do you think it will wait until I have used up all 32 characters? Well, let's try something like this. How about I just type ABC and then press the enter key? Okay. Well, it returns right away. But I asked for 32 characters. I asked to read 32 characters, and it has just read 4 in this case. Well, this is because of the standard in the console is cooked. Okay. Yes, that's a technical term, cooked.
Like a turkey.
Okay, cooked means it is not really reporting all the characters that you type. For instance, the backspace key is not reported. It allows you to do all kinds of editing on the line before it actually accepts that line by the enter key, and then it just feeds the entire line to the program, including the line feed key. The line feed key is actually a part of the key here too. So if that is the case, how do I know how many characters were actually read? Because it seems like when I request to read 32 bytes, it can read in fewer than 32 bytes. So how do I know exactly how many bytes we have just read? Well, as it turns out, when it returns, when int, when the interrupt instruction returns, in this case, EAX also has a meaningful value. EAX is coming back indicating the number of characters actually read. So in this case, if I use IREAX, I should see ABC line feed, 4 characters. It does. Okay. Are we really sure that the line feed character is one of the characters that we are reading back? We can check buffer. So we want to go to buffer. We are going to print 4 things. Each one is a byte, and I want to print it as a character. And we'll do this at buffer. And this is what we have read. 97 is the code. This is actually in decimal, but that's the ASCII code of lowercase a, and that's why it displays lowercase a in quotes. And then we have B, and then we have C. 10 in decimal also specifies the ASCII code of the line feed character, which you normally know as \n in your C and C++ program. Are we doing okay so far? So we are reading in line by line in this case because it is code, so it only feeds you a line at a time. Are we doing okay with this program? All right. But when we have a program that reads, when I give you the next homework assignment, it will be a chore to have to do this, typing, again and again and again to test whether your program is doing what it is supposed to. So we can do a little trick here. So I can do a test.in, which is an input file for testing my program. So in this file, I can have ABC, enter DEF, enter GHI, and then a bunch of enters, empty lines, and then the last line we'll just put an exclamation point as the last line. This is my test input file. Okay, and when I test my program, I can do something like this. I can say gdb read, okay, and put a breakpoint first because otherwise I cannot re-examine the buffer. So I'll go ahead and put a breakpoint on line 13, just like before. But when I run the program, I'll do something a little bit different from before. I'm going to specify something like that. I'm going to run the program specifying less than and then test.in. What it does is to tell the debugger and say, when I run the program, standard in is no longer mapping to the keyboard of the console. Instead, use this file test.in as the input. Use it as standard in. So whenever I read from file descriptor 0, which is standard in, it's actually reading from the file. So this is a really good way to test your program because it ensures consistency. Okay, every time you run the program, you're reading from the file. So as long as you don't change the file, you're testing the program exactly the same way. You have the same test case. Are we doing okay so far with this? So we'll go ahead and run the program. Now it hits the breakpoint on line 13. I want to see what buffer has, but before we even do that, let's see how many bytes it has read. It read 16 bytes, not 4. That's because when you're not reading from the keyboard, the TTY, teletype, console, it is not cooked anymore. In other words, when you're reading from a file using the redirect symbol, line feed, and backspace, they have no special meanings anymore. Those bytes, even though they are control characters, will just be read exactly the same way as any other bytes. Well, I don't believe you. Let's take a look at the content of the buffer. X/, in this case, we'll display all 32. 32 BC, and this will be the address of buffer. Okay, this is what the buffer has. As expected, we have A, B, and C, and the line feed. But we also have the next line, because we have D, E, F, and its own line feed, and then we have GHI and its own line feed, and then we have a bunch, two empty lines with only 2 line feeds, and then the exclamation point of the last line, and then the line feed after that. What about the other locations? What about these locations here? They remain they're not touched by the read operation. They were just basically what they were before. In other words, the read operation is not null terminated. Do not look for the null character because it is not null terminated. Are we doing okay so far with this? What if I give it an empty file?
It's gonna read forever.
Well, let's try it. It's not that easy, it's not that hard. So we'll just say touch empty.txt. The touch command just updates a file's last modification date. And in this case, because empty.txt did not exist, it would just create a file that has 0 bytes, an empty file. So empty.txt is truly an empty file with no content. If you want confirmation, this confirms it. Okay, it has 0 bytes. So we'll go ahead and do the experiment again. This time we do gdb read, put a breakpoint on line 13, and we'll read from empty.txt. Well, the first thing we want to do is to check the value of EAX because it tells me the number of bytes that has been read. It's 0. It makes sense. Okay? And, well, if it is reading in 0 bytes, I don't even have to bother to look at buffer because it should not have been changed. Okay. Just one more thing to illustrate before I let you go, because this is also very important, because it's closely related to what we have done so far, and it is also an important thing. So we'll go ahead and change my program again. And what I'll do is I'm just going to copy and paste it. In other words, I have 2 copies of this exact code. It's reading twice. Each time it's trying to read 32 bytes. Okay? And let's see here. We'll put a breakpoint here. We'll put another breakpoint here. That's good. Okay. So we reassemble, we link, and then run the program. But this time I want to, oops. GDB. Put a breakpoint on line 13, which is right after the first read attempt. Put another breakpoint on line 19, which is right after the second read. Okay. And this time we'll run the program using my test.in as the input. Okay. Now we already know that when we are redirecting from a file, it is not cooked, which means it will just read as many bytes as it can and then stop. Okay. And the file isn't all that big. This file only has 16 characters. So the first read, which is requesting to read 32 characters, would have read the entire file already. And it will report back that it has read 16 bytes, just like the last time we ran the program this way. But what about the second read? I have a file that has 16 bytes. The first read has read all 16 bytes already. The file pointer is already at the very end. So when I attempt to read again, what do you think should happen?
0.
It should read back 0 bytes. Very good. Okay. But we want to confirm that. So we are at our first breakpoint right now. EAX reports that it has read 16 bytes. It's perfect. And then we continue execution with the program and attempt to read past the end of the file. It does not generate a segmentation fault because it is okay to attempt to read past the end of file. It's just that it cannot read anything. So what this means is when the read operation returns, and in EAX it returns a value of 0, it means that you are at the end of the file already. There's nothing else to read. Okay, and that's how you can terminate a loop that you would use to read a file. Because otherwise, how do you know when to stop processing a file? This tells you that you're at the end of the file. Are we doing okay so far with the read operation? The write operation is really just as easy. It's system surface number 4 instead of 3. You specify a file descriptor that is an output file, like 1 is standard out, and then you specify the location where you want to print stuff from instead of read stuff into, and that's it. So I think the read operation is actually a little bit more complex than the write operation because you actually have to interpret EAX after the system call. Whereas with the write operation, you should interpret that too because sometimes you can request to write 256 bytes, but the system may only be able to write 16 bytes. Remember the printer example? You're trying to dump a whole big bitmap to your poor 9-pin dot matrix printer, and it cannot handle it. So it is possible in that case that you will try to dump out 64 kilobytes of bitmap, but the printer that has a smaller buffer will only accept 8 kilobytes. So in that case, EAX will also return with 8 kilo or 8192 to indicate that of the 64K that you want to dump to the printer, only the first 8K successfully made its way to the printer. Then you have to figure out the logic to feed in the rest. All right, are we doing okay so far with the read and write operations? The next homework assignment is going to have some read-write operation and base conversion at the same time.
Very nice, very nice. Did we get it over the weekend?
No, we're taking a break, remember?
Yeah, I remember. When are we getting it, next week then?
Sorry?
Next week then, sometime?
Yep, next week. Next Tuesday, after this homework, the current homework assignment is due. Yeah. Then we'll move on to this one.